Welcome back everyone to EGME-333 Fluid Mechanics. In this video we are going to be discussing the conservation of mass and momentum. Let's first begin by discussing the conservation of mass, which states that the time rate of change of the system mass remains unchanged. Mathematically, we can express this by taking the material derivative of the system mass and setting it equal to 0. Or we can write this in its integral form by taking the material derivative of the volume integral of rho dV, where the volume is defined by a control volume. And we set this expression equal to 0. By using the Reynolds transport theorem, we can obtain an equivalent integral form where we can expand the material derivative of the system mass to equal two separate integrals, a control volume integral and a control surface integral. And again, we set that expression equal to 0. By moving the control surface integral to the right-hand side, we can rearrange this expression as taking the control volume integral on one side and equating it to negative of the surface control volume, where the left-hand side represents the net mass increase inside a control volume, and the right-hand side represents the net mass flow into the control volume across the control surface. The idea behind the conservation of mass is basically that the net rate of increase of the mass inside a control volume is equal to the net mass flow entering the control volume across the control surface. In its general form, the conservation of mass is composed of two separate integrals, a control volume integral and a control surface integral. But we can simplify this expression by assuming that the flow is one-dimensional at both the inlets and the outlets. Doing so, it'll help us simplify the control surface integral so that we can simply reduce it to the summation of one-dimensional inlets and outlets. So, if we go back to the general form of the conservation of mass equation, we can rewrite the control surface integral as simply being the summation of the net mass flow going into the control volume across the control surface minus the net mass flow coming out of the control volume across the control surface. We can further simplify this expression by assuming that the flow is steady. When we assume that something is steady, essentially the partial derivative of anything with respect to time is automatically set equal to 0, because that quantity becomes independent of time. By applying the steady flow assumption to our problem, we can also simplify, or in this case, eliminate the left-hand side of the expression by setting the control volume integral to 0. So we can simplify the conservation of mass for a case that is steady with one-dimensional inlets and outlets as simply saying that the net flow going into the control volume equals the net outflow coming out of the control volume. Recall that the mass flow, m dot, is equal to the fluid density times the local velocity times the cross-sectional area. So we can simply expand out that expression to reflect these quantities instead. Next, let's shift our focus over to the conservation of linear momentum. When we consider Newton's second law, it is frequently written as the sum of all forces is equal to the mass times the acceleration, where F is the net exerted force on the body of mass m, and bold A is the acceleration of the body. However, the more general form of Newton's second law is should be written in terms of linear momentum, the product of the mass m times the velocity vector, bold capital V. So the acceleration term, we can rewrite it in terms of velocity, where the sum of all forces is equal to the mass times the rate of change of the velocity vector with respect to time, dv dt. Now, if mass is treated as a constant, we can move in the constant into the derivative, where now, instead of dealing with mass times dv dt, we're taking the derivative of mv, the momentum, with respect to time. So we can see now that the sum of all forces is equal to the rate of change of momentum. We can then argue that the sum of all forces acting on the system is equal to the time rate of change of linear momentum of the system. So when we discuss the conservation of linear momentum, it is essentially an application of Newton's second law of motion to a fluid element, where the momentum of a system is given to us by the following control volume integral, where it is the volume integral of the product rho capital V of dV. I'll highlight here that the bold capital V represents the velocity vector, whereas the V in the dV represents volume. So we can define the conservation of linear momentum as the time rate of change of linear momentum of the fluid mass is equal to the net external force acting on the mass. Mathematically, we can express this as the total rate of change of linear momentum inside the system is equal to the sum of all forces acting on the system. Note that momentum is the product of mass times velocity, where velocity is a vector. So when forces act on a flow field, those forces can change both the velocity magnitude or direction. Alternatively, if we see changes in the velocity, direction, or magnitude, then consequently there needs to be a force responsible for that change. So if we consider a fixed non-uniform control volume, we can utilize the Reynolds transport theorem to expand out the rate of change of momentum of a system into the following two integrals, where again we have a control volume integral plus a control surface integral, where the first term represents the time rate of change of linear momentum of the system. This is equal to the time rate of increase of linear momentum inside the control volume plus the net outflow of linear momentum through the control surface. If we combine this with Newton's second law, then we obtain an integral form of the conservation of linear momentum. Note there are a couple things we can do to modify this expression depending on the flow or problem that we are analyzing. For example, if the control volume is moving with a constant velocity, then the equation must be modified to include the relative velocity, bold capital W. And it's the relative velocity of the flow relative to the velocity of the control volume. Also note that F represents the sum of all forces acting on the control volume, and so the control volume should be considered as a free body. Third, note that this is a vector equation. Both integrals consist of vector quantities. Therefore, we have to consider all three directions. For example, we can break up this expression into the x direction, and similarly, we can break up this expression into the y direction and the z direction. Lastly, I do want to review a lot of the common assumptions that are utilized when working with the conservation of linear momentum. The first one is steady state. which, as we previously stated, anything where you take the partial derivative with respect to time, this is set automatically equal to 0. Therefore, by working with the steady state assumption, this eliminates the control volume integral. So it simplifies the conservation of linear momentum to the following expression, where conceptually we can think about it as the net momentum outflow is equal to the sum of all forces. Another common assumption that we make is that we assume one-dimensional inlets and outlets. This assumption allows us to simplify the control surface integral by writing it as the summation of all of the net momentum flux coming out minus all of the net momentum flux going in, and ends up modifying the conservation of linear momentum in this fashion. Lastly, we can combine both the steady state and one-dimensional inlets and outlets to simplify both integrals and obtain the following expression for the conservation of linear momentum.